So, like I said, I'm counting this as a help session, and so I'll get your attendance before you leave. I will also, I'm recording it, and I'll post it to the website, so if you're not here, you can get credit, but if you're not here, you're not hearing this, unless you're watching the recording, and then you're hearing it. But I'm going to record both classes, but you cannot get double credit. So like if you send me notes for both help sessions, that's fine if you want to do that, but you only get single credit, okay? First thing I want to do, I'll address your questions in just a bit, but the first thing I want to do is to work through that fourth free response question. Remember, I've told you that this is the, the fall 22 exam. You don't have this in the back of your workbook, unfortunately. Do you? Is that fall 22 in the back? That's fall 21, isn't it?
Yeah, fall 21.
Yeah. Fall 22 is a better one to look at. Although you'll find similar free response on other exams, but I have worked through numbers 1, 2, and 3 on this exam, and we can do those again. But now I want to work through number 4. We've done problems similar to this, but this is what's going to be on your free response. There's something really similar to it. First thing we're going to do is just write down everything that we know, and I recommend that you do the same. I have a yo-yo that's traveling in this circular path. It tells me that it's spinning at 6 radians per second. So I should be able to, I can determine what variable that is just from the units. So since it's in radians per second, that is going to be omega, 6.0 radians per second. Also, it says it has a mass of 0.20 kilograms, and that the radius of its path is 0.5 meters. I meant to have 2 sig figs there, so let's keep 2 sig figs the whole way. And now I want to know, what is the centripetal acceleration of this? The centripetal acceleration, if you recall, is equal to v squared over r. I think that is on your equation sheet. Is that right? I think it is. You might confirm that for chapter 7. You sure? Okay, yeah, so this is AC. What you have on the equation sheet is the equation for centripetal force, which is MAC, which is mv squared over r. All right, so it's sort of, that explicit equation isn't on there, but you know, the AC is on there. The equation sheet is what you'll have. You'll have 5, 6, and 7 on it'll be on the front of your bubble form. Just make sure that you're familiar with it. There are a couple of things, we'll address that in a bit, a couple of things that aren't on the equation sheet that you'll need to know. Anyway, so AC is equal to v squared over r. Remember, we did this substitution in class, where because v is equal to omega r, I can rewrite this as omega squared r. If you want, you could come up here and calculate what v is. Just say v is equal to omega r, and then put that in for v. Whatever you want to do, use that alternate form of the equation, or actually calculate the linear speed. Either way is fine by me. Anyway, I'm going to do it this way. Omega is 6. That's squared times r, which is 0.5, which is 36 times 0.5. That's 18 meters per second squared. Then for part B, I want to know the tension at the top of the yo-yo's path. So for this, I'm going to draw a picture. And you know, I could change this to be at the top of the path or at the bottom of the path, or I guess even at the side of the path. So you need to be prepared for any one of those. Let me show you what that would look like. Imagine I have this ball that's spinning around in this direction. At the bottom of the path, which is where I'm looking, I want to know what is the tension, the tension in the string at the top of the path, which is what I want to know. Notice there are 2 forces acting on this ball, or the yo-yo. There's the weight, and there is the tension in the string. I also want you to recognize that the acceleration here is in the downward direction. So my centripetal acceleration is going to have a negative value. So if I write Newton's second law, that is the sum of the forces is equal to ma, and my a in this case is the centripetal acceleration. The sum of those forces is going to look like this. Negative Fw plus Ft. Negative because both of those forces are in the downward direction. Both Fw and Ft. Or you could have written that as negative Fw minus Ft. That would have been the same thing. Is equal to m times negative AC. So that value for AC that I found, the 18 meters per second squared, that's the magnitude of the centripetal acceleration. But notice at the top of the path that it has a positive value. I mean, excuse me, at the top of the path, it has a negative value because the centripetal acceleration is always towards the center of the circle, right? That's what centripetal means, center seeking, that is always towards the center of the circle. So if I want to find FT, I say, well, first of all, this negative will cancel out with that negative, and FT will equal to MAC minus FW. So that's going to be M, which is, what, a half 0.2 kilograms, times AC, which was 18 meters per second squared, minus the weight, which is going to be 0.2 times 10, or 2 newtons. I got the weight. I said FW is equal to M times G. That's equal to 0.2 times 10, or 2 newtons. All right, so that gives me that 3.6 minus 2, 1.6 newtons. Okay? That's how I would find the tension in the string at the top of the path. Might also ask you the tension at the string at the bottom of the path, and it's going to work out much the same way, except some of your signs are going to change. Watch how it's different. I'll do it in green. In this case, my tension and my weight are going to be upwards, right, when it's at the bottom, or excuse me, not upwards. My tension will be up, and my weight will be down. So this is FT, and this is FW. Also notice that my centripetal acceleration is in the upward direction. So do the same thing. Sum of the forces equals MAC. And that's going to be FW, or excuse me, FT minus FW equals to M times positive AC. My centripetal acceleration is positive in that case. So if I want to find FT, that's going to be FW plus MAC, which in this case is going to be 2 plus 3.6, which is going to be 5.6 newtons. So at the bottom of the path, the tension in the string is bigger than it is at the top of the path. Have you ever, played with a yo-yo and you've done this round the world thing? I'm not sure. Can any of y'all do that? Do the round world thing with a yo-yo? Any of you? Chloe? You can do it, Ashton? Really? Yeah. So you know that when your yo-yo goes up to the top, that sometimes the string even just goes slack, right? That there's no tension in it at all because it's not going fast enough. So the tension in the string is definitely lower at the top than it is at the bottom. And this is why, because the tension and that weight are opposed to one another, and it causes a greater tension in the string. Okay, there could be one other way that I would change this. Instead of having it neither at the top nor at the bottom, I could ask you, what is the tension at the side? And in this case, it actually becomes quite a bit easier because I have two forces still. I have the tension in the string, FT, and I have the weight in that direction, and my centripetal acceleration is in that direction. In this case, I would say the sum of the forces in the x direction, which just includes FT, is equal to M times AC. So in this case, FT would equal to MAC. That would be 3.6 newtons. That the weight doesn't contribute at all to the centripetal force because the weight then is perpendicular to the centripetal force. All right? Any one of those three. I wouldn't ask you, at any other, like here, I wouldn't ask you that. That becomes more difficult. But it'd either be at the top of the trajectory, or at the top of the path, the bottom of the path, or off to the side. A lot like hold on, Juliana. It's a lot like the Ferris wheel problem. It's basically identical to the Ferris wheel problem that we did a couple days ago, and it's also a lot like the elevator problem. Is the tension bigger or smaller if you're going up or down in the elevator? That's from chapter 4. Juliana?
Can you explain how you got that omega squared times r?
Yeah. So we did that a couple days ago. We said that AC is equal to v squared over r. That is our centripetal acceleration. However, we can relate our linear quantities to our angular quantities in this way. V is equal to omega r. So if I take this and substitute it in right here for V, then I get a different expression for AC, which is omega r squared divided by r, which if I cancel out one of those r's, I get omega squared r. So AC is also equal to omega squared r. Again, I guess that's not on your equation sheet. So if you forget that, this equation is on your equation sheet. Recognize that this represents the acceleration, and then you can just, calculate v from the omega and r that's given to you, and then you can plug it into that equation. Does that answer your question? Yes. Okay. I encourage you to draw the picture. Oh, I'm sorry, Emily. Go ahead.
For the one for the side, why didn't you use the force weight?
Yeah, so the one on the side, I didn't use the force weight because remember in Newton's second law, back in chapter 4, we would say that the sum of the forces in the x direction is equal to max, and the sum of the forces in the y direction is equal to may. Because I know that my acceleration here is entirely to the right, that's the right, yeah. My acceleration is towards the center of the circle, and my tension is towards the center of the circle. I only need to consider my x forces. There is something going on the y forces, but I don't need to worry about it. I only need to be concerned about the x forces. Okay? Notice here, my biggest tension is at the bottom, my smallest tension is at the top, and on the sides, that tension is somewhere in between. Right? My smallest tension was 1.6, my biggest tension was 5.6, and then on the sides, it's just mv squared over r, 3.6. Okay? Yeah, I'll be practicing that problem. I know that you look a little bit like deer in the headlights, but you have, 5 days or so to practice it. Make sure that you can do it. There is at least one instance of this problem in fall 22. There might be another occurrence of something similar in previous semesters. Is that not? Are you saying no? You're not sure. Is that true? Does that problem exist elsewhere? I'm not sure. Anyway, it is in fall 22, so you can practice it on that one. And there might be a homework problem that's similar to it. Alrighty? Be prepared for it, okay? What I was going to say is, too, that you're not required to draw the picture, but I find it really helpful with my signs to draw the picture. So I really do recommend that you get into, as you're practicing, that you draw that picture and then draw your acceleration vector, say, oh, is this positive or negative? Because that's often where students are going to get messed up, is with the signs, right? There's really just a negative sign that's different between those answers. Yeah, Joey.
For the one in blue, I saw that it started as a negative FW plus FT equals M minus AC.
Right.
How did you get it to turn into the positive?
Oh, I multiplied both sides by -1. Let me rewrite that. So I had negative FW plus FT is equal to M times negative AC. That was what was right here. But if I multiply both sides by -1, so if I multiply this side by -1 and I multiply this side by -1, it gets rid of those negative signs. See, I know it looks a little strange because I had this negative embedded, but I could have written that negative over here just as fine. But I didn't, because I was attaching it to the AC. The negatives come from the direction, right? In that case, just to remind you, the negative that was in front of here came because these two vectors were in the downward direction. And the negative that was right here came because the centripetal acceleration at this point is towards the center of the circle. With something in a circular path, the centripetal force is always towards the center of the circle, but with something in a vertical circular path, it changes signs too. If it's overhead, well, I guess it changes signs in the x as well. Yeah, never mind. But anyway, it changes direction continuously, the centripetal acceleration. At the top, it's pointing towards the center of the circle, which is down. At the bottom, it's pointing towards the center of the circle, which is up. The signs. It's the signs. That's the hard part on that problem. Okay? Y'all okay on the rest of the free response? We to work through any one of those? Other problems that you want me to work through in the multiple choice? Yeah, do you want to look? Actually, let's look. We can come back and do this one, but let's look at some of the others, which I think actually might be different, maybe more difficult, like number 1 here. Is that okay?
Yeah.
We can go back to the free response if you want. But let's look at this one. In fact, this one reminds me that there are a couple of equations that you need to know, but you do not have. I think that you probably do know them. One of them is the equation for friction. The frictional force is equal to mu times the normal force. And at least for an object on a horizontal surface where the weight is pointed down and the normal force is pointed up, the normal force is equal to the weight. And I remind you that that's also equal to mg. Okay? Which, if I'm asking you to find the normal force, it will be on a flat surface and there won't be any other forces. So for the sake of this exam, if you need the normal force, it'll be equal to the weight. Okay? You will see some inclined planes, like in that free response, but you won't be required to find the normal force. No, gosh, I don't think there are any components of vectors. Well, when you calculate the total work by a force, where you do the FD cosine theta, that is taking the component of a vector, but it's sort of embedded in that equation. Anyway, so those are 2 equations that you'll need to know that are not on the equation sheet. That's from chapter 4. All right, so here I have a block that has a mass of 4 kilograms. It's sliding across a floor with a velocity equal to 2 meters per second. It's going in this direction. However, there's a force that's acting on it in that direction. So as this object moves across the floor, that frictional force takes away energy. And I want to know how far does it travel before it comes to rest. This way I think to approach this is to say that this object starts out with some kinetic energy. At the very beginning, it has a mass, it has a speed, it has kinetic energy. As it's going along, it loses the work that's done by friction. And then finally it comes to rest, and so the end result is that it has 0 energy. So it starts with kinetic energy. You take some of that energy away. In fact, you take away all of that energy because it comes to rest, and then it stops. So it has no kinetic energy. So let's say 1/2 mv squared minus the work done by friction, which is going to be the force times the distance over which it acts, is equal to 0. Now, notice here that when I write this negative right here, I'm already assuming that the force and the displacement are in opposite directions. That's why I give it a negative value. So, I'm looking here for D. So I can go ahead and solve this for D. Or if you want to put in numbers now, that's fine. It'd be 1/2 mv squared divided by F. 1/2 of the mass, that's 4, times V, which is 2 squared, divided by the frictional force. Oh, I don't give you the frictional force. So here I need to determine what is the frictional force. It's equal to mu times the normal force. Mu is 0.2. That's the coefficient of kinetic friction. And the normal force, we said, is equal to the weight. That's going to be 4 kilograms times 10 meters per second squared, or 40 newtons. So that's going to be 8 newtons. So this is the frictional force then is 8 newtons. Half of 4, that's equal to 1 meter. Okay? Definitely going to see 1 or 2 problems like that. You have one on the free response, but you'll have it 1 or 2 in the multiple choice as well. Okay? That's helpful, Tatiana? Yes. You're going to see something like that. So be prepared. There'll be 2 or 3 instances where you have friction. On the free response, at least 1, and the multiple choice, I think more. Y'all, so I've told you this, let me just reiterate it. Heavier towards chapter 5. I think there are 7 or 8 multiple choice questions from chapter 5, but then there's 2 free response questions, isn't that right? No, look, there's 1, 2, 3, 4 questions, because numbers 1 and 2 are both chapter 5, so that's 7, at least 11 questions of the 28 are from chapter 5. And then the remainder are split between chapters 6 and 7. Chapter 5 is just a longer chapter. Chapter 6 and 7 were much shorter. Okay? Other particular questions?
Same test. Can we do number 10?
Yeah. Okay, can we do number 9 and 10? Is that okay? Gonna see questions like both of these, okay? Both of these, numbers 9 and 10, are collision problems, but they just go a little bit differently. I really recommend that you draw a picture if you encounter either one of these problems, which you will encounter problems that are similar. So draw a picture. Let's start with number 9. So I have a 1 kilogram block traveling to the right. 1 kilogram traveling to the right at a speed of 3 meters per second. It collides with a stationary 2 kilogram block. 2 kilogram, V is equal to 0. Then the 2 kilogram block now has a speed of 1 meter per second. What is the final velocity of the 1 kilogram block? So we need to make, I tell you that the speed is 1 meter per second, but that's going to be 1 meter per second to the left or to the right? It has to be to the right, right? Because the net momentum up here is to the right, and so the net momentum here also has to be to the right. So I'm not going to get this run into a stationary object, and then all of a sudden this thing starts moving to the left. So, but you do have to discern that. So this now has a speed of 1 meter per second, and now the 1 kilogram block, I want to know what is its speed. All right? I say that the initial momentum is equal to the final momentum. That's going to be 1 times 3, m times v, is equal to, did I write that 0 there? No, this should have been a question mark right here. What is the v? 1 times v plus 2 times 1. So that's 3 minus 2 is 1, so v is equal to 1 meter per second. So D is the right answer. 1 meter per second actually positive, that means it's to the right. I don't ask that here because I'm just asking for the speed, or I asked for the velocity, but it's positive 1 to the right. Okay? It's a collision problem. You're going to have that also in the free response. Remember I told you that that free response would actually be a perfectly inelastic collision. That's when the two objects do what? They stick together and they move off at the same speed. That'll be your free response. Let's look at number 10 too. Also, a collision problem. It's just a little bit different. We've done one like this. There was one in the concept test. I think we did one in class as well. Here you have two cars. One is 2,000 kilograms. It's moving at a speed of 4 meters per second. I actually don't tell you the direction. Turns out it doesn't really matter. We'll assume it's positive and to the right. The other car has a mass of 6,000 kilograms, and it's stationary. Now the two cars connect, and they move off at the same speed. So I can imagine now that I have two cars that have a total mass of 8,000 kilograms, and they move off. Well, I know that it's going to move off in this direction. I want to know what is that speed. So I have 4 times 2,000 equals 8,000 times v. And I want to know what v is. V is going to be equal to 1 meter per second.
That's just PI equals PF.
Yep, that's just PI is equal to PF. Anytime you see these collision problems, that's going to be your governing principle, the conservation of momentum. There will also be collision problems, like on the next page, where I ask you something about the force. So listen, if you see the word force in a problem, that should key to you or make known to you that I'm looking for this. I know that the force is equal to delta P over delta T. And then I can use that's a rewriting of Newton's second law in order to find the force. And that would be for number 11 and for number 12. Okay? You want me to do those or y'all cool? I'll do number 11 and we'll see if y'all want to do number 12, I can. So delta P is equal to the mass times my change in speed. And so the key here is going to be determining the change in the velocity. Notice that VF is equal to 12 and VI is equal to 8. So that means that delta V is going to be 12 minus 8 or 4. The mass is 3 kilograms. Now 12 minus 8, that's equal to 12 kilogram meters per second. That's just my change in momentum. But if I want to know the force, that's going to be delta P over delta T, which is 12 divided by the time that it requires, which is 6 seconds, which is going to be 2 newtons. Okay? Notice in number 12 that I also have a collision that occurs in 0.1 seconds. But this is a situation where the object collides into something and bounces off. So here my velocity initially is 10. My final velocity is 2 meters per second. So what is going to be my change in velocity? It's going to be 12, right. Whenever it rebounds, the difference is actually the sum of the two numbers. Because if I have a final velocity of, well, let me draw it. So I have a car, it's traveling at 10, and then it rebounds at 2 meters per second. So VF would equal to negative 2, and VI would be equal to positive 10. Then it's going to be negative 2 minus 10, or negative 12 meters per second. Or you could say positive 2 minus negative 10 would be equal to 12. Either way, I don't give you the directions left or right, but the end result is that the magnitude of your velocity is going to be the sum of those two numbers. Notice that that's different from what I did in 11, because in number 11 it wasn't a rebound. It just slowed down. It accelerated. All right. Particular questions? Let's scroll through some of these. Let's look at our rotation things. You're going to see a number of these, like number 17, number 18, number 19. Look back in the back of your workbook. Are there any particular questions you would like to work in the fall 21 exam? Yeah, Logan. Number 12 in that exam? Okay. Okay. You'll have collisions in your multiple choice, but you'll also have them in your free response. Your free response is going to look pretty darn similar to this one. Okay? So recognize this is a perfectly inelastic collision. That means that my final mass is going to be 6 kilograms because that 4 and 2 kilogram mass stick together. I start with the principle or the law of the conservation of momentum. PI is equal to PF. That is 2 times 3 plus 4 times VI is equal to 6 times negative 6. The positive 6 is the mass, the negative 6 is the velocity, because it's moving to the left. Be careful with your signs, so when something's moving to the right, the velocity is positive. When it's moving to the left, the velocity is negative. So I have, what's that, negative 36. VI is equal to negative 36 minus 6 divided by 4. That's 42. Negative 42 divided by 4. Was it 11? Was A is the right answer on that one? D?
Wait for 12. I've got 8 here.
Yeah, A is the right answer. Yeah, it should be A is the right answer. So I get negative 10.5 or negative 11. That's like your free response, but you'll also see collisions like the ones we did earlier in the, in the multiple choice. Let's see. Number 16, remember impulse, that's just change in momentum. So that would be 2. Notice the speeds change. So it's going to be 2 times the sum of those 2 speeds. Since they change direction, I get a rebound. So it's going to be 2 times 7 or 14. Number 16. Number 13 is one like we just worked. Make sure you know your units. I have at least one question that asks the units, the basic SI units. So be able to do that for momentum and for energy. Yeah, momentum and energy. I guess that's really all that I could ask you. All right. If you want to look into exam 4 as well, exam 4 has rotation problems on the back of your book. I'll go and open it up. So look at exam 4. The first probably 4, 5, or 6 of those are probably rotation problems. Oh, this is backwards. This problem, angular velocity of the rotating Earth, we actually did that in class. Remember, it does 1 full or 2 pi radians in 24 hours. I think the answer is D there. Be able to know your unit circle, 90 degrees would be pi over 2 radians. Remember the example we did with the clock? Remember the clock moves in the negative direction? Might ask you. I will ask you, in fact, something like that. Number 3 here is like the problem that we did with the yo-yo. So you're not going to see a Ferris wheel in your multiple choice, but you will see it in the free response. So make sure you can do that. Let's do number 5 here. This is number 5. This is a kinematics problem. So as with most of our problems, we start just by writing down what we know. It's initially at rest. That tells me my initial angular velocity is 0. I apply a torque, or torg, I misspelled that, it should be a Q. And it accelerates at 2 revolutions per second squared. Don't worry about the torque. We haven't got to that yet, but you don't really need to know the torque or what it is. All that you do know is that it accelerates at 2 revolutions per second squared. And I want to know how long does it take the merry-go-round to complete theta of 2 revolutions. I do know that theta is equal to omega naught t plus 1/2 alpha t squared. Omega naught is 0, so that whole term goes away. And it looks like I know alpha and I know theta, so I have everything I need. This is a pretty simple problem. I say 2 revolutions is equal to 1/2 of 2 revolutions per second squared times t squared, and so t is equal to 1 second. You might have problems too when you see examples of these in some of the past exams where it requires a 2-step process where you have to first find the time and then you have to find whatever it is that I'm asking for. We did that back in chapter 2, but you could see that again here. That might be one like this one. Let's see, is that right? No. Let's do this one there. Yeah, actually quite a few of these problems are from chapter 7. An object is spinning at a constant rate. It slows. That's important. It tells me that alpha is equal to -2 revolutions per second squared. And it takes 6 seconds, so t is equal to 6 seconds. And that the final angular velocity is 0. And I want to know what is omega naught equal to. I do know that omega equals omega naught plus alpha t. Let's see, do I have everything I need for that? I know t, I know alpha, I know omega. Yeah, so I'm just solving there for omega naught. It is important there, though, that your alpha be negative, that it has this initial velocity, and then it's slowing down. So my omega naught is going to be positive, my alpha will be negative. So I can solve this 0 equals omega naught plus alpha, which is negative 2, times t, which is 6. Omega naught equals 12. All right. Either this would stop at question number 10. Particular questions, y'all? Or just particular areas, momentum, or energy, or work energy? Logan? Oh, do I have to convert it to radians? The one that I just did? Oh, yes. I would have to convert that into radians, so 12 revolutions per second. 1 revolution, 2 pi radians, that's 12 times 6. I don't see that answer here. Doing that right? I must have changed it along the way. I'm not sure what I did, because the answer would be like 70 or so radians per second. What's the answer in the back? Do you have it? Let's see, number 6. B. Yeah, I must have either changed the units or changed the question somehow. But yeah, this would be about, I don't know, 12 times 6 is about 70 radians per, about 70 radians per second. I don't think that I had any like that where you just have to look at the units to know what the answer is. I'm pretty sure that it is. Not very nice, is it? Is that nice? Is that nice? Not really. But do look at the units. It is helpful to look at the units in the options. It'll help you think about the answer, what it should be. Okay? Other questions, John? How y'all feeling about this exam? Number 5. I'll tell you. Oh, we have like 20 minutes left. Oh yes, it's the square root of 2. You're right, Tatiana. So sorry, I didn't see that square. Yeah, it should be 1.4 there, which would be B. Sorry, I was rushing. Don't rush on the exam. Make sure you check every number as you go along. I know that's tedious, stressful, but read every word, check every number. They're all important. Okay? So, probably our easiest exam, but if you're not prepared, it's not going to be easy. So make sure you get prepared. If you need to chat over Zoom or on the phone or over email, just send me an email. But tomorrow morning, we're leaving pretty early. I'm not going to get back until late Friday afternoon. But then, if we need to Zoom Friday night or Saturday morning, I'm going to Lafayette on Saturday, probably around 8 or 9. But if we need to talk, or even if we need to meet, Roger or whatever, we can meet and help you. I'll be available or not available. But please do contact me if you want to see me. I am available. All right. I know this conference is still time, so that's what it is. And then also, listen, I'm not going to be here on Monday for the exam. I told y'all that. I'm going to HL for a road trip. So, are you upset? Listen, I think that y'all get our secretary, Christy, is going to be in here proctoring your exam. So you know what to do. You'll have a seating chart when you come in. There'll also be one here. Sit in your appropriate seats. She won't know your names, but she'll know if you're in the wrong seat. And she's like a Hawkeye. I see like every time she comes to my class, she catches somebody that's cheating on an exam, and she documents it. She tells me about it. She is tough. So just Don't think just because, oh, the secretary's in it, she's not watching. And you know what? Your integrity anyway is a lot more valuable than any points on an exam. Am I right about that? Your integrity is, come on. She was joking. But your integrity is really important than any points on an exam. So please, do your own work. All right? All right. Don't leave unless I get your name. I'll stand by.